All right, this mini lecture is going to describe two different types of periodic waves. So remember in the first description, our little mini lecture on wave descriptions, I introduced the idea of a pulse, a wave pulse, so just something that sends a burst of energy down through a medium. And then the periodic wave, so the one that travels through the medium, it has a wavelength and a frequency and an amplitude. Well, the pulse has an amplitude too. But the wavelength and the frequency and the period, something that we kind of think of as a wave traveling through the medium. I'm going to take that periodic wave and I'm going to split it up even more. I'm going to describe two different ways that a wave interacts with the medium that it is traveling through. These two waves, the first is known as a transverse wave, and we're going to contrast that to what we call a longitudinal wave. All right, longitudinal wave and transverse wave. Now, the easier one is the transverse wave. So imagine that I have a slinky and I move one end up and down of the slinky. We see this wave travel down the slinky. So if this were my slinky and I move that slinky up and down, we see this wave travel along the slinky. However, the slinky itself is traveling up and down. So if I look at a particle, a point on that slinky, at one point in time it's maybe at a crest, and at the next point in time, let's see how good I am at drawing the opposite, right? At another point in time, there we go, it's at a peak. So the medium itself is traveling up and down. So any location in that medium is traveling up and down. So the wave is traveling along the medium while the medium itself is being displaced up and down. And then once the wave passes by, that medium, remember, is no longer displaced. That's sort of that definition that we talked about as a wave. So when the wave direction and the medium are perpendicular to one another, we call this a transverse wave. Now, is there another way I can make this energy through a medium that disturbs the medium in a different way? Well, imagine that slinky again. And instead of going like this, I go like this. And if you can imagine, you hopefully maybe have played, well, maybe not hopefully, but perhaps you've played with a slinky in the past. If you imagine if I start to do this, I push it, it kind of gives this woo, woo wave down the slinky. That's what we call a longitudinal wave. So let's imagine this is my slinky. This isn't a wave, this is the slinky itself. And I do a compression, and then I have this space, and we see a wave motion, compression. We call this rarefaction, compression, rarefaction, compression, where the wave is traveling in that direction and the medium is traveling in a parallel direction. So again, if you imagine this point on the slinky, it goes back and then comes back to its center, forward, and then comes back to its position. So it's traveling, as the energy passes through it, it's being taken in the dimension of the energy travel and then refracts back to its location. And we do in these longitudinal waves, and I remember that by going along the medium. A longitudinal wave travels along the medium. We get these periods of what we call compression and rarefaction. Sound waves behave in this manner. Water waves behave in a transverse manner. Sound waves behave in a longitudinal manner. We get a compression of air, and that compression of air, that energy travels through in a compression, rarefaction manner until it hits our inner ear. And then it hits water, well, it hits bone, then it hits water, and then the cochlea does its thing. So two different types of this periodic motion. Visually, transverse waves. The medium travels perpendicular to the wave motion. Longitudinal waves, the medium travels parallel to the wave motion. All right, good job.